Hey guys, it's IDW, and today we're going to be moving on from just incrementing, that is, adding 1 to a number, like what I went over in the last video. Just to remind you, there you go. Adding 3 plus 1 is 4. Today we're actually going to be moving onwards towards full addition, in which we're going to be taking two numbers, and not just one number and adding one to it, and adding them together. So, I think that when I actually watched back over the footage that I took of me building this thing, I thought that I had a pretty good explanation. Maybe I'm going to be reviewing a few of the things that I didn't think I got down too well in this recording session, but for the most part, if you've seen it, you're probably going to be able to understand this no problem. So what I'm going to do is I'm just going to, first of all, make an XNOR gate, because you might be wondering why I'm just jumping into this and not doing some more theory work. And really, we've done all the theory work that there really is to do in this series. And now I'm just going to be showing you how to use that theory work in order to build an adder. So right here, we have the ability to add two numbers together. They have to be 1 bit long, and it'll give us the result that we need for this bit. So, what? Oh, never mind. There we go. Anyways, so what we have right here is basically a way that we can add the first two numbers that we're going to have. Since we're going to have a whole, in our initial adder that we end up building, we're going to have one of these for every single bit. This is going to be the first input, and this is going to be the second input. So if I was to build another one of these right here, the next bit of the first input would be here, and the next bit of the second input would be here. And the reason we're doing this is we're using this XOR design right here to actually add the two numbers together without generating a carry yet. So, from what we have right here, I'm just going to stack this, because at this point it starts to get a bit weird, because we have to throw in carry now. Because, I mean, 1 plus 1 does not equal 0. It equals 1, 0. 1 in the next bit. So now, let's just stack it 3 times. So we're going to have a 4, 0, 0. There we go. Anyways, so now what we have is we have a whole bunch of XORs lined up next to each other, but they can't interact with each other. So basically what we've done, if we look at this addition problem right here, is we've added these two numbers together, and we've gotten this result. The next result that we need to find is whether or not we're generating a carry. That is, we're having a carry that we need to add on to the next bit. So the simple way to do this is to just build an AND gate. And as it turns out, this design actually has an AND gate that it needs to work. So I'm just going to take this right here and say that this is the AND of these two values. And you might be wondering, well, it doesn't look like this one right here. And the answer is, you're right, it doesn't, but the concept is still the same. You have both of your inputs, they're getting inverted with a redstone torch, they're both being ORed together into the same place, and they're all powering these torches. So technically, this is in fact an AND gate. If you want me to prove it, that input on, no output. That input on, no output. Only an output up here if both of them are on. So now what we're going to have to do is we're going to have to add it to the next bit. So what I'm going to do to... Actually, first of all, I'm going to do that, just because I wanna... don't really have to explain that right now, but anyways. So now I'm just going to take this wire right here, and I'm going to bring it down. And if I can remember, I can remember how to do this. So basically what I've done now is I've taken the carry that I added from these 2 bits, and now I'm going to add it into this bit because technically its place value is worth equal to this one. So I need to add it to the sum that I get from these ones in order to get the finalized carry calculation. Well, the finalized result. So that's exactly what I'm going to do. I'm going to add them together using an XNOR again. And I can actually use the basic XNOR without doing the little modification that I did to the other one. And I'll fix that later. Why not? I have all the levers that I'm going to need. Anyways, so this should be the result of these 2 bits. But there is one last thing that we have to keep in mind, and that is that, first of all, I'm going to need to stack this thing. And second of all, if both of these are on, then it can actually generate a carry that will move on to the next bit. So we do actually need to use the AND gate again in order to calculate this carry. But other than that, we really can just wire this up like this. And we can keep doing this onwards for eternity. So yeah, I'm just going to pause my recording right now and build it off camera, just to save video time. So I'll see you in a second. Alright, so we're back. And as you can see, I have just finished off everything. Just one last thing that came up, and that is that at the very end, as you can see, there was, you have a carry line that actually goes out of it. And that's sort of like, if you were to add 99 plus 99, you would technically be able to get 3 digits instead of 2. And seeing as we've divided this all into sections, one of each bit, you can actually get numbers that are higher than the numbers that you put in to this thing. So that's what the carry out is for. It represents the numbers that you can't actually represent with the number of bits that you're given. However, if you were to count this, then you would see that we only have 4 bits right here. That's because I haven't actually included this one yet, because I want to show something really quickly off to you guys. So since these 2 have been added together, there isn't actually any carry data that can affect them. So normally we would just do something like that, right? Well, actually, there's something that you can do called a carry in, which you can use to, which is used in subtraction, is probably its most prevalent uses, but there's other stuff, like incrementing a number without needing to actually save 1 into your memory, and then do the thing with the 1 that you have in your memory. So in terms of CPUs, you can actually build a carry in, and then XOR that with the data that you have right here from the first bit. And so then we just finish up the XOR. And so yeah, if we wanted to right now, we could actually add a carry in into this, and it would add 1 to it. And as you can see, if we were to add 1 to that, it would carry over to the, and of course I haven't put a torch up here, which I should, just because it gets powered by those. It doesn't get powered by those because it's an AND gate. So then it'll carry over to the next bit. So yeah, now if I want to just do a fairly standard problem, 5 plus 3, so that would be 5 is 1, 0, 1, and 3 is 1, 1, and I should get 8 as my answer, and as you can see, I got an 8. So that proves that this is in fact an adder, and yeah, there are some design features that are not perfectly desirable about this, but we'll be getting into those later. for now, this is just an working adder, and that's all that matters. So, see you guys next time.